we're going to talk a bit more about these eigenmodels I've just introduced to you, and actually talk about how they can be used now to do some classification in the machine learning sense. So this is where the computer vision comes in. We're also going to see some other applications of this eigenmodel, this what we call principal component analysis, to do things like visualize high-dimensional data and sort of simplify data by projecting it into a low-dimensional space. It will all become clear. Okay, so remember last lecture, lecture before last, sorry, we built this simple sky classifier, and the weakness of this classifier was the simplicity of the model, which was just computed by averaging the RGB values of pixels. And remember, we had this issue whereby which we were just computing the distance from that model of every test point and thresholding that distance. And that implicitly defined then a spherical decision boundary at that threshold value, beyond which pixels were classified as non-sky. And we talked about how a spheroid, a sphere in that space, can't fit, often can't fit a natural data distribution, because it tends to be the case that distributions you measure in practice aren't nice and sphere-shaped, they're actually ellipsoid-shaped, and therefore it would make sense to have a ellipsoid decision boundary. Okay. So, in order to compute a distance function that allows us to have a ellipsoid decision boundary, we need to consider not just the mean of these points, but also the distribution of these points. And as we discussed last hour, the distribution or the shape of that distribution can be modeled well by this covariance function, okay? And we saw how the covariance can be decomposed into eigenvectors and eigenvalues that model the eigenvectors point along the directions of variation of the data, and the eigenvalues tell us how much along each of those directions the data varies. So notice actually how I've used the notation sigma squared, and then the subscript here indicates which of the eigenvalues it corresponds to. And these eigenvalues in this example are three-dimensional, so the matrices are 3 by 3 in both cases. So the eigenvalues are the variances along each of the eigenvectors. And therefore the eigenvectors form this data-dependent basis set. Right. So, looking at this classification problem then, we're going to introduce a new form of distance measure. Instead of using the Euclidean distance from the mean, which is what we were using before, to classify these sky or not sky, these pixels as being sky or not sky, what we're going to look at instead is this new measure of distance we call the Mahalanobis distance. And the Mahalanobis distance is a way of measuring how far we are from this data distribution in units of standard deviation. Okay? So, this distribution of points here, I've drawn a ellipsoid around them, and we can imagine that ellipsoid being a contour marking out a certain number of standard deviations from the mean of that distribution. And that contour will model the shape of that distribution. It'll be an ellipsoid. Actually, there is no hard boundary here. This is just a sort of an illustration, okay, indicating where points that are one standard deviation, let's say, are from that mean. But we could draw another sphere at points of 2 standard deviations or 2.31 standard deviations or whatever. But what we can see is that this point here and this point here that have the same Euclidean distance, L2 norm from the mean, have different Mahalanobis distances from the mean, because this point here is clearly maybe 1, 2, maybe 3 standard deviations from the mean. I know it's just a rubbish PowerPoint drawing, but this point here is clearly within 1 standard deviation of the mean. So this Mahalanobis distance function, this measurement of distance in units of standard deviation, is going to be a more robust way of measuring the distance of a point from the training data distribution. Everyone follow? Yeah. So, having calculated that Mahalanobis distance, and I haven't told you how to do that yet, that's the subject of this hour, okay, we can threshold that distance just like we thresholded the Euclidean distance. But because the Mahalanobis distance is measured in units of standard deviation, it's taken the shape of the distribution into account. Every time we threshold that distance, we're defining an ellipsoid that is greater and greater volume centered about the mean. So our pipeline then is going to be pretty much the same. We take our training data, our patch of sky pixels, we measure those pixels' location in RGB space, we build a model, but in this case we're not just calculating a mean, we're calculating a covariance, because as we'll see in a moment, the Mahalanobis distance is calculated using the mean and the covariance. And then having calculated the distance, this Mahalanobis distance, we threshold it just as before at some threshold we've decided using our ROC curve process in order to come up with an appropriate threshold, which then lets us classify pixels as being sky or not sky. Great. So how do we calculate then this Mahalanobis distance? Well, we use this equation. Okay, so the Mahalanobis distance, which we're going to call d here, is calculated through this equation. And I'm going to talk through this equation, and we're going to see why every term of this equation exists the way it does. If I've got a test point x, and I want to figure out how far that point x is from this distribution, then first of all, I'm going to have built an eigenmodel from the distribution. So I've got a mean, and I've got a u and a v. The first thing I'm going to do is subtract the mean from that test point x. I'm then going to pre-multiply that test point x by u transpose. I'm then going to pre-multiply the result of that by v inverse. And then that will give me a vector. I'm going to calculate the magnitude of that vector, the length of that vector. That's what these bars mean. And that's going to give me actually the Mahalanobis distance squared of that point x from that distribution that's been described by the eigenmodel, which remember consists of the mean, the u, and the v, the eigenvectors and the eigenvalues. Does that make sense? Well, it probably doesn't make sense yet, but do you get the process? Any questions on that? Okay, so let's see why the Mahalanobis distance is calculated in this way. Why does it work? Well, let's look at the operations in turn. What is happening when I subtract mu from this x? Well, let's start off by talking about what x is. X is a vector quantity. It's a three-dimensional vector that exists in my RGB feature space, in my three-dimensional feature space. So x, as a vector, is the offset of this test point from the origin of my feature space. That's what the vector x is, right? It's a vector pointing from the origin to that point. The amount I had to walk along red, green, and blue to get to this point. When I subtract mu from x, I'm redefining x not as an offset from the origin of this space, but as an offset from the origin of the eigenmodel, which is mu, the mean of the data distribution. You want to follow? Okay. The next thing I'm going to do is pre-multiply that vector there, which is x minus mu. I'm going to pre-multiply it by u transpose. What does u transpose do? Well, u, remember, is an orthonormal matrix. So u transpose is the inverse of u. Now, thinking back to last lecture, we talked about the passive interpretation of a matrix transform. Who remembers what the passive interpretation is of pre-multiplying a point by a matrix? Remember we talked about PD pre-multiplied by D took us out from point P in the reference frame D into the point PR, which is the point P in the root reference frame. So pre-multiplying a point by a vector converts a vector defined within that reference frame into the root reference frame. Here we're pre-multiplying by the inverse of a matrix. And the passive interpretation of that is converting a point defined in the root reference frame, as it is here, into an arbitrary reference frame that's defined by u. So taking this point, x minus mu, this vector here, which is defined in terms of these axes, i.e. our root reference frame, By pre-multiplying it by U transpose, we are casting that point into the arbitrary reference frame defined by the columns in U. Yes? The same thing. It's the same thing. The question is it the transpose or is it the inverse? It's the same thing because U is an orthonormal matrix. Yeah? The columns in U are of unit length and they're all orthogonal to one another. In other words, the eigenvectors. So this U is defining a basis set, as we saw in the previous lecture, that is oriented to the spread of the data. So now our point, which is x minus mu pre-multiplied by U inverse, U transpose, whatever you want to call it, okay, that point now is defined entirely by the reference frame of the eigenmodel. Yeah? Where the origin is mu, and these axes now are the eigenvectors. Does that make sense? We've cast the point into that reference frame defined by the eigenmodel. Now let's look at the next step. The next step, we're pre-multiplying by V inverse. Now V, remember, has got the eigenvalues in it, okay, which is the variances along each of the eigenvectors. Because V is a diagonal matrix, the quick way we can calculate the inverse of a diagonal matrix is just simply go down the diagonal, just do 1 over every entry down the diagonal. Yeah, take the reciprocal of it, okay? So V inverse is another diagonal matrix. What is a diagonal matrix? It's a scaling matrix. So if we're pre-multiplying by V inverse, and by the way, notice that V transpose and V inverse are different things here, because V is not an orthonormal matrix. By pre-multiplying by V inverse, we are scaling that point. What are we scaling it by? We're scaling along each axis in inverse proportion to the eigenvalue or variance along that axis. Yeah? So, in our previous slide, when we were just considering U transpose x minus mu, this point was defined within a reference frame that had been dictated by the eigenmodel. This red vector, the principal eigenvector, pointed in the direction of greatest variation. So it had a large corresponding eigenvalue. When I pre-multiply by V inverse, I'm scaling, I'm warping this space, I'm contracting it proportionate to the value of the eigenvalue along that corresponds to that eigenvector. Yeah? So this eigenvector here had a large eigenvalue. So 1 over that large eigenvalue is quite a strong, a small scale factor, so it will shrink quite a lot. Yeah? Yeah, in fact, it is. It's exactly like normalizing it. So what's happening is points that were spread out more in this distribution will be contracted in more than points that weren't very far from the mean in terms of their standard deviation before. So it has the effect that it is contracting the points in so that this vector now, if you were to calculate its magnitude and threshold it would be reasonable to put a spherical decision boundary around these points. So when I calculate the magnitude of this vector now, the magnitude of this is the magnitude of this vector defined not only in the space determined by the eigenmodel, by the eigenvectors and the mean, but also has been warped in inverse proportion to the amount of spread along each of the eigenvectors. So it is effectively we could whiten the data so that it is now in a sort of spherical distribution. Okay. Why? And the length of that vector then is that Mahalanobis distance. Why is it giving us d squared? Why is it not giving us d? Remember, we said the Mahalanobis distance is defined in units of standard deviation. Variance is standard deviation squared. Because the elements in V are variances, this is in units of variance. So if we want to get the distance in units of standard deviation, we would square root all of that. for shorthand, we just write d squared equals that. Does that make sense? So that's how the Mahalanobis distance gives us a measure of distance from the data distribution in units of standard deviation. Right, before I go on to this slide, has anyone got any questions about that? Yeah. Yeah, that's a fair question. What if your data distribution not only was ellipsoid, but it was actually like banana shaped or something? Okay, well that's what we call nonlinear distribution, and then it would not be appropriate to use an eigenmodel. In fact, what we tend to do, we don't do it on this course, but what we would tend to do is model that distribution in piecewise form using multiple eigenmodels. It turns out that this eigenmodel is expressed as a mean and a covariance. We can think about that model as being a Gaussian distribution in that space. Yeah. So actually, when we're building an eigenmodel, what we're doing is we're calculating a best fit Gaussian in high dimensional space to that data. If we end up modeling a banana-shaped distribution, we use multiple Gaussians. We build Gaussian mixture models, but we don't cover that in this course because then we'd have to talk about something called expectation maximization to fit it, and we haven't got time for that. Yeah. Oh well, yeah. So okay, that's the question is what's the radius of the sphere? This sphere doesn't actually exist. Okay, this is me drawing a circle in PowerPoint that's meant to illustrate a contour of equal distance d. It doesn't have a particular radius. It's meant to just indicate that if were I to threshold this distance as I would normally to make a decision, sky or not sky, I would choose a value, and then that would implicitly define a spherical decision boundary. But because I've done that warp, it's okay to do that, because following this warp, the data goes from ellipsoid shape to spherical shape, and then I can do my threshold. Yeah. Yeah. No, the threshold could be from 0 to infinity, depending on how big your distribution is. So let's. Oh, I see. You mean after normalization? Right. Okay. So yeah, that's a good question. So the question is, what would the range of the threshold be? Clearly, you could threshold this distance at any value between 0 and infinity, but it is usually appropriate to use a threshold something like 3. Why? Because if you look at a Gaussian distribution, which is what the eigenmodel basically is creating, 97% of the area under a Gaussian is within 3 standard deviations of the Gaussian. So if you were to threshold the Mahalanobis distance, which conveniently is expressed in units of standard deviation at 3, then you would be thresholding such that 97% of your training data is within the threshold choice. Okay, so sometimes if you look up the Mahalanobis distance in a textbook, you'll see it expressed using this equation here. It actually does the same maths. What we're doing here is we're actually taking a point. Oh, that should be a transpose there. Sorry, I don't know why it's not. I guess I omitted that. So there's a transpose on that. So this equation here, we're taking this point, pre-multiplying it by U transpose. Yeah, and let's forget about the V inverse in the middle. That was U transpose there, which it should be. We're taking a point, rotating it into an arbitrary reference frame by pre-multiplying it by U transpose. Then we're multiplying it by U, so in effect, these two cancel out. And then we'd be taking then an inner product of this vector and this vector. So we're basically taking a dot product of x minus mu with x minus mu. Hopefully you know if you take the dot product of two vectors, sorry, if you take the dot product of a vector with itself, you end up with a value which is equal to the square of its magnitude. Yeah? So that's what we're doing here. That's the dot product. That calculates the magnitude of vector x minus mu. That does the same thing. Remember there's a t there, typo. Okay? But by putting v inverse in the middle, we're scaling that space before we calculate that magnitude. So it has the same effect. This is a little bit like when we looked at how we scale on an arbitrary axis in that first example last hour. Okay, where it's like performing a rotation, then a scaling, then an inverse rotation. So why have I put this equation up? Because it just looks more complicated. Well, actually, there's an interesting thing we can note about this equation. because if I hadn't made a typo and there was a t there, we notice that this is the same as this, okay, here, which is an expression for the inverse of C, the covariance matrix. If I take my covariance matrix C and I decompose it to U, V, U transpose, a quick way of calculating the inverse of C would be just to invert the V in the middle. Okay, so U, V inverse U transpose is C inverse. So this means that this expression here is just simply C inverse. So actually, I can calculate the Mahalanobis distance without doing any eigen decomposition at all, without even building an eigenmodel. All I need to calculate the Mahalanobis distance is the mean and the covariance. I don't need to build the eigenmodel, but it's worth talking about it because otherwise you don't understand why the Mahalanobis distance works the way it does. Yeah. Yeah. Yeah, I think I said several times that was a typo and there's maybe a T there. Yeah, thanks. Any other questions? Okay. Okay, so now we're going to do another demo, and this is a demo that I made several years ago when I was cooking my dinner of some peas. So what we're going to do, and you get to do this in the lab as well. I did have something other than peas as well. Right. So what we're going to do is we're going to load up the image of the of that pan of peas. So let me just find that image. Just give me a moment to find that. Right. Okay. So there's the image. Now, the mission here is to find the region of the image that is peas. Okay. So what we're going to do first of all is we're going to build an eigenmodel just using a picture of peas. So let's load up that image, which is going to be target underscore peas. Okay. There it is. There's an image of peas. So first thing we're going to do is build the eigenmodel. So the first thing we do is we're going to load the image in. And I'm just going to make it a little bit easier for visualizing by just dividing the values of that image. Instead of the range of RGB going 0 to 255, it's going to go 0 to 1. Okay, so there's my eye, there's my image, a whole bunch of pixels. I'm going to reshape that image into some data. So I'm going to say, let's reshape the red channel of that image into a big long line, and then one row. Oh, hang on. Let me just get this right. It's going to be red, then green, then blue as the three rows in that matrix. Right, so there we go. There it is. So that X is like a really long matrix. Okay, it's basically containing columns which are red, green, blue for every pixel in that training data of peas. Okay. Now we're going to calculate the mean, which, as you recall, we just used the mean command for, so it's just calculating the average red, green, and blue to make a three-dimensional vector. And now we're going to subtract from that data set X the mean from every column. Okay, so what do we have there? It's 8,000 pixels. Okay, so there's my mean subtracted data. Now what I'm going to do now is calculate the covariance of that mean subtracted data. Okay, so that's the covariance matrix. So we've got C and we've got our mean. Now we're going to build our eigenmodel by saying U and V is the eigendecomposition of C. So that mean and that U and that V, okay, is our eigenmodel of that data of the peas. Yeah. Now what I'm going to do is load up the image of the whole kitchen, and we're going to reshape it as before. Okay, so now that is all the pixels in that larger image of the kitchen, RGB for the three rows, okay? And what we're going to do now is calculate the Mahalanobis distance. Oh, hang on, that's not quite right, is it? Because I need to divide it all by 255 to make the RGB in the range 0 to 1. Yeah, so that's my image of the kitchen. That's my data now. Okay, they're RGB. And now what I'm going to do is calculate that Mahalanobis distance. So what do we do to calculate the Mahalanobis distance? The first thing we do is subtract the mean from each of those pixels. Doing this right, yeah. Okay. Then we're going to multiply each of those vectors by U transpose. Yeah. And then we're going to multiply each of those vectors by the inverse of V. And that's going to give us a matrix, let's call that G. Okay, so that now is the result of V inverse U transpose X minus mu. Now what I want to do is calculate the magnitude, the length of each of those vectors in order to get that Mahalanobis distance squared. So what I'm going to do then is go D equals, what was that called, that matrix? G. Okay, there's no short way of doing that. So let's say it's there we go. So that's D squared. If I'm really lucky, when I reshape that, that will have worked. So let's reshape. So that's my Mahalanobis distance squared. So let's make an output image by reshaping that D to the same size as my image, which was 240 by 320. Right. Okay, so that image there is an image where every pixel has been shaded a grayscale value in proportion to its Mahalanobis distance squared. So actually what I probably should have done is square root that. That's a bit better. We'll turn the lights off. That's a bit easier to see. Might need to go full dark for this one. Okay, so can you see how the darkest pixels are those of the P's? That's because those pixels have the smallest Mahalanobis distance to that eigenmodel that I built from the colour distribution of the P's. Whereas other objects in the scene, like this yellow, I don't even remember what that was. I think it was some sort of pipe detector for the walls, got to do some DIY. That's very different colour to the P's, so that's very bright white. Okay. So if I were to threshold then that image at some value, it's a bad threshold choice, let's try that. Yeah, there we go. It's not a bad job anyway. So you can see we sort of picked out the region of the P's. Maybe it's better to have done it the other way around. Okay. Right. Okay. Yes. Well, the steps I just went through there were exactly these steps here. I subtracted the mean, I pre-multiplied by U transpose, and I pre-multiplied by V inverse, and then I calculated the magnitude there of the vectors and then square rooted them. It's not really much difference really in the two, I would say, because that's implicitly a squaring operation, that first line of that slide. Okay, has anyone got any questions about what went on there? So we were building a colour distribution of that patch of P's, that training data. We built that eigenmodel, in other words, computed mu, U, and V. And then we went through every pixel in here and we calculated the Mahalanobis distance from that data distribution in order to create a field where every pixel was proportional to the Mahalanobis distance, which then we thresholded. Clearly I chose a better threshold in that slide than I had time to search for here. Oh yeah. Okay, so yeah, so in this case, because the training data was so, yeah, I actually slightly cheated when I did this demo. So actually what you might notice, if you've got a very keen eye for the P's, I actually just cropped a little square from that, so I really cheated there and actually used my test data as my training data. I shouldn't have done that, okay? So my distribution was super, super tight, so I had to, in the end, it wasn't a reasonable approximation, 3 standard deviations. So, keep a point like that. Okay. Any other questions on it? Okay, so let's talk just in the last 10 minutes about some other applications of this principal component analysis, this building of an eigenmodel. I actually gave this example a minute ago when I talked about the, an hour ago, whatever it was, when I talked about a distribution of points lying on that front desk there in this three-dimensional world. That was an example of a world that was three-dimensional, had 3 axes, but the distribution of points was scattered along a plane, a 2-dimensional plane embedded in that 3-dimensional world. So I had this example here. And I talked about how the principal eigenvector then, in this example, would be pointing all the way along the desk. The second eigenvector would be orthogonal to that, pointing also along the desk. And then the third would be pointing either upwards or downwards of the desk. That third eigenvector, that third eigenvalue associated with that third eigenvector would be 0 because there was no variation in that direction through the space. And that tells us something about the data. It tells us that the data, although it's 3-dimensional, only has 2 degrees of freedom in it. It varies only in 2 different ways. Okay. So I won't have time to run the demo, so I've just got it on the slide here. So I can replicate that using this example here in MATLAB. Let's imagine that I create 100 points in 2 dimensions, and I add a third dimension that just contains 0. If I then build the eigenmodel using these steps, so I calculate the mean, I do the mean subtraction from the points, and then I calculate the covariance and decompose it. If I look at the u and the v that I get, I'll see that I get eigenvectors that are aligned to basically the x, y, and the z axis of the space, if you want to call the first, second, and third axes that. But you'll notice that the eigenvalue associated with this third axis is 0. We call that the null space. Okay, it's the direction defined by the eigenvector or eigenvectors in the space that has no variation along it. The concept exists in higher dimensions to any dimension. Let's suppose that I take 100 points in 5-dimensional space, and I add a 6th dimension that contains, in this case, some random points that have been scaled down quite considerably. Okay, I calculate the eigenmodel. Here and now, I'm working in 6-dimensional space, so I've got 6 eigenvectors and 6 associated eigenvalues. Look down here, in this case, it's come from MATLAB, so here we've got a very, very small eigenvalue. The others are quite large. This tells us that most of the variation in this data occurs along 5 degrees of freedom, even though there's 6 variables here in the data. Okay, so usually when we're looking, it's quite useful, as I'll explain in a moment, to look at the null space of data. And when we look for the null space of data, there are various techniques we can do. We can look for eigenvalues that are 0, but usually they're not exactly 0. So what we usually do is either threshold the eigenvalues, we choose to keep a certain number of eigenvectors and values, or what we might do is we might go from the largest to the smallest eigenvalue and stop when we reach, say, 97% of the data. I don't know how many of you would have encountered the properties of matrix called trace. It's something you can just compute. It's a number you can compute about a matrix, just like the determinant is a number you can compute about a matrix. I guess you all know how to compute the determinant of a matrix. It turns out that the determinant of a matrix is the product of the matrix's eigenvalues. And the trace, if you ever computed that, is the sum of the eigenvalues. So it's a shorthand way to compute the product and the sum of the eigenvalues, respectively, of a matrix. So what we might do is calculate 97% of the trace, or sum of the eigenvalues, and then we might walk from the largest to the smallest, stopping when at the threshold of 97%. And that would allow us to keep most of the eigenenergy, as we call it, of the distribution. In other words, most of the information of the distribution. What is the point of calculating this null space? Well, I said it was useful. Why is it useful? Well, ultimately, our job, we've been talking about today, is building a classifier. And to build a classifier, we need to build a model of data. So if I suppose I have some data here in one-dimensional space, and I want to build a model on that data, as we've discussed, we calculate the mean and we calculate the variance of that data. Just with 3 data points, we can get a reasonably good approximation for mean and variance of this data. Now, if I was working in 2 dimensions, I'm now going to have to compute the mean and the covariance of this data to model its centre and spread. But I'm going to need more data points in order to get a good estimate of that spread. If I'm working in 3 dimensions, I'm going to need even more data points to get a good approximation in my eigenmodel of the data's centre and spread. And as I keep adding more and more dimensions to my space, I'm going to need more and more data points in order to get a good approximation of the distribution in my eigenmodel. Remember, these data points in the context of classification, these are training data, and the dimensions are the features of our space. So the more features, the more things I measure about the world in my machine learning problem, the more training data I'm going to need to collect. This is what's sometimes called the curse of dimensionality. So if I were going out with my weather example and I was measuring, 100 things about the world to figure out if it's a sunny or rainy day, thinking back to Monday, okay, it might be that, I measure 100 things about the world, but there's only 5 degrees of freedom in that data. It might be things like ice cream sales and soda sales and things like that are highly correlated. So there's actually only like 1 degree of freedom for, say, 2 or 3 features. In that case, what I'd find is if I took that distribution and built the eigenmodel, it would have a null space in it because the data wouldn't have as many degrees of freedom as it had features, as it had dimensions. That would mean, in order to build my eigenmodel, I could get away with using less data. So, what we can do actually is we can exploit the null space to project our data down into a lower dimensional space that doesn't lose any information, doesn't lose any degrees of freedom, or at least loses very little, but we lose dimensions. This is what we call projecting into a lower dimensional space. Do you remember back, we were working with this idea of the passive interpretation, where pre-multiplying a point by a matrix that defines a basis set, cast that point from that arbitrary reference frame into the root reference frame. And I told you that the inverse goes the other way. And I've said several times this property that if M is orthonormal, then we can just shortcut this inverse process and just use a transpose. Let's suppose that I've taken an eigenmodel of some data and I've measured 3 things, 3 features. But when I do my PCA, I figure out that actually there's a null space here. What I could do is come up with a truncated version of U, where I throw away all of the eigenvectors that have a very low or 0 eigenvalue. In other words, I discard the null space. This matrix K here is that. It's U with the vectors thrown away, the eigenvectors thrown away that correspond to low eigenvalues. What I could do now is instead of taking my points P and pre-multiplying them by the inverse of U, or U transpose equivalently, to cast them into my reference frame, what I could do instead is pre-multiply it by this truncated version of K inversed. But notice we can't invert K because it's not square. But luckily we can, because K is orthonormal, so we can use our shortcut and we can just say K transpose. So when we want to take our data in high dimensional space and cast it into a lower dimensional space, in this case go from 3 to 2 dimensional space, but not lose any information, any variation in that space, I can pre-multiply by K inverse, by K transpose, where K is this truncated version of U that contains only the eigenvectors that are not the null space. Does that make sense? That's equivalent to saying, if I take this data in this three-dimensional room that was scattered on top of this table, I can represent that distribution in just 2 dimensions without losing any information, which is clearly the case because there's no variation in the 3rd direction. That was the null space. So yeah, that's just the message there. The final thing I want to show you is another useful application of principal component analysis, which is to project high-dimensional data into low dimensions, just like I just showed you, but for the purposes of visualization. So in this example, we've got a guy here in a motion capture suit, which is like an antique version of the suits they tend to use now for movie special effects. Each one of those markers helps us track the joint angles of the person. So when the person's in a particular pose, there's a bunch of joints, and each joint can be expressed, it turns out, as a X, Y, and Z rotation. So for every joint, we can measure 3 things. So for a particular pose, let's say the pose has got 12 joints, each one we're measuring 3 things about, we can represent a pose as a point in the 36-dimensional space, 12 times 3, yeah? What we might do is you might capture a cycle of someone walking, and every frame of that video is going to be a point in that space. And probably because they're walking, it's going to create some sort of cyclic pattern in that space. Because this pose is the same as this pose, same as this pose, yeah? Wouldn't it be great to be able to view that trajectory? Well, we can by using exactly the same trick. We can build an eigenmodel of that data, and we can throw away all but the 2 or 3 largest eigenvectors, by which I mean the eigenvectors that have the largest corresponding eigenvalues, because of course eigenvectors always have unit length. Yeah? And then we can project, using that K-inverse trick, to project our data down from high dimensional space into lower dimensional space. So this, in fact, is such a capture projected into 3 or 2-dimensional space using that process, where the arrows indicate movement between points. And you can see, you can visualize then that high-dimensional data in 2 or 3 dimensions, which of course is necessary if you want to actually plot it on the screen and do some analysis. So, in summary then, in this lecture we recap the components of an eigenmodel and their mathematical and geometrical interpretations. We looked at how we calculate this thing called a Mahalanobis distance, which gives us the distance from an eigenmodel in terms of units of standard deviation. And I explained why it's calculated the way it is in terms of reference frames. And we saw how we could apply that eigenmodel not only for supervised classification tasks, but also to reduce the dimensionality of high-dimensional data, either to make it more compact in a lower dimensional form to avoid that curse of dimensionality, or for visualization of high-dimensional data. Right, and you'll be applying some of those techniques in the lab this week. So, thanks very much.